The Niagara Escarpment.
Yep.
On the Bruce Peninsula.
Yep.
On the west side, it slopes, and there tends to be coniferous trees, especially cedar. On the east side, there's jagged cliffs.
Yep.
And tends to be, what's the word? Coniferous. No, not deciduous. They lose their leaves. And it includes oak trees. Why?
Yeah. So you asked me a question about geology and biology, so I'll do my best to answer. But the Bruce Peninsula, to a geologist, it slopes to the west, so that we call that dipping. So if you imagine a book, you have a book, and you just do like that. That's the face of the escarpment here, and then that's the dip surface on top. And usually that dip surface is very thin soils, a lot of exposed limestone, and cedars like that. So when we're out prospecting geology in other parts of Ontario, as soon as we see cedars, we know we've got limestone around. I think the other side, the deciduous trees, there might be more shelter on the steeper slopes from north winds and so on. So I think it's a combination of geology setting the table, as it were, and then the vegetation responding to the local slopes and whether it's west or east. So it's probably a bit of what we call, mesoclimates along the Bruce Peninsula.
Okay.
So Nick, I don't know if you can see the Q&A I think it's probably at the bottom of your screen. There's several questions in there if you want to have a look at those and answer as you see fit.
Yes, okay. I can see some comments open. I can only see a comment.
Okay, there might be a Q&A as well. I think there's 16 questions in there. If you can't see them, I can read some out.
Yeah, just me read them out, and I'll have a go at them.
So a question from Lois Palmer: are MSGL's erosional features as well as depositional, like drumlins?
Yeah, that's a really good question. There's a big debate raging in geology, and our group think they're primarily erosional because we can trace their evolution from drumlins. So drumlins and MSGLs tend to hang around together, and you can trace what we call intermediate types between the two. So without the new LiDAR data, we never saw these things. And it's just another illustration of the importance of getting good topographic data. So we think they're erosional, and you might say, okay, where does all the debris go underneath the ice that's eroded off the drumlins? Well, it builds moraines. So underneath the ice, it's resting on sediment and rock. And when it's resting on sediment, it's an overpressured situation, what we call overpressured, because you have water in the sediment and you have a great weight, the ice sitting on top. So it raises the water pressure, and the sediment, the upper part of the sediment, will deform and be driven along underneath the ice by the flow of the ice itself. So it's a very thin layer, probably about 50 centimeters thick, very, very thin. There's been a lot of work done in the Antarctic using geophysics, using drilling, and that's referred to as deforming till. And we think that's the material that it's like concrete, fluid concrete moving underneath the ice, and we think that's being driven along, and that is the material that's doing the erosion. It's like an abrasive sheet. And I mentioned in the talk the science of tribology. If you want to Google that, tribology, there's a ton of work, and just go under images. If you do Google searches on any aspect of geology, just look at images, and you'll pick out some surfaces that have been imaged by tribologists, engineers, and you can see grooves, you can see drumlin-like features, and they're attributed to what's called an erodent layer. It's debris that's worn off the surfaces in contact. So it's happening in your car, on any bearing surface. If it's not well lubricated, they'll begin to degrade under friction. And then that material is a very thin layer, and it actually furthers the erosion of the layers. And if you look at the surfaces that are produced, they tend to be grooved and drumlin. So it's yet another illustration of how friction gives rise to the same basic morphology, but on different scales. And we've had a lot of luck to looking at faults. A fault in geology is where blocks of rock are moving past each other, and they can be quite small scale features, or they can be huge things where subduction going on, where one tectonic plate's been driven down below another one. And again, you see the same basic pattern of grooves, drumlin-like features as a product of friction. So in a glacial realm, they're produced under ice. In tectonics, they're produced by big blocks of rocks sliding past each other. And in the man-made realm, they're formed by man-made surfaces sliding past each other. So you might be interested to know that hip replacements, joint replacements, when they wear, and if you look at the fine scale surface, you see the same basic pattern. So it's characteristic of all friction. So if your joints are acting up today, you know why.
Eileen asked for a reminder of what MSGL stands for.
Okay, MSGL, yeah. Mega scale, that means really big. Mega scale. Glacial, produced by ice. And lineation, any longitudinal feature, lines produced parallel to ice flow. So mega scale, glacial, lineations, which I never introduced. There's a guy called Chris Clark, 1993. And geologists use the term MSGLs to save time.
Brian Rogers asks what work is being done in our area, Northern Grey County.
Oh, well, right, LiDAR data. I'm surprised nobody's asked me, how do I go about getting LiDAR data? Where is it available? And it's, at the moment, fairly expensive. And it's only flown very sporadically across certain parts of Canada. There's huge areas that don't have it. Large areas of the States, they've gone gung-ho on LiDAR mapping, less so up here. And so our work is driven geographically by the availability of data. And even Google Earth, if you get on Google Earth, you can often see MSGLs in the landscape. So you know they're there. And Grey County has nice drumlin fields, got nice marine systems and MSGLs. So once LiDAR data is available, there's the opportunity for a very nice study up there, actually. But it all depends on the availability of data.
So Brian also asks, is if these advanced LiDAR maps are available to the public?
No, they're not. That's a good question. Most people think, well, I can just download these images from a government website. The only thing you can download is the digital data. It's what we call a data cloud. Very, very large data sets. And there's an awful amount of processing involved to generate the images. So we run into the problem where people see the images and naturally they're not aware of all the computing power and the time that's involved in generating the images. So they're not something you can just readily pluck from a website somewhere. It may be one day. We've got ideas of doing an atlas because some of these images are beautiful. They're like art, and I detect sort of heightened interest in them just talking to you tonight, and I think the public would be interested in an atlas of those parts of Canada where LiDAR data is available. But they're the result of a lot of work.
Yeah, looking at them myself, I thought they were very artistic. They sort of they reminded me of the electron scanning microscope images in just the sharp detail that you have.
Yeah, that's a really good analogy. Actually, it's comparable to the new images that scanning electron microscopy generated. Yeah, 60s, 1970s. Yeah.
Sort of a whole new level of detail.
Yes, exactly.
Win user asks, we have a lot of potholes in our area. Can you give us some up-to-date information on their formation?
Yeah. Some are potholes. They belong to a population of landforms called karst, K-A-R-S-T, which is derived from an area in Yugoslavia which is dominated by limestones, and where underground water flowing through joints, cracks, dissolves the limestone, creates caves, and then the roof of the cave will collapse and you get a surface depression like a crater. Swallow hole, pothole, or they can form too in your area on the top of the Niagara Escarpment, where you can't see it, but the escarpment is actually creeping. It deforms because you've got a steep cliff there, so the rock wants to expand into the space, and so you get these famous crevice caves up there, and sometimes what's called a sinkhole is actually the surface expression of a joint controlled crevice cave. But they're all typical of karst. Having said that, we talked about glaciation, and there isn't much karst in southern Canada, even though we've got huge areas of limestone. I've always puzzled over that, and it's because the climate of the last couple of million years has been too wet, and water tables are close to the surface, so the limestones remain saturated for the most part, and you don't get that area where water's traversing from the surface down to a much deeper water table, which you need places like Florida, Kentucky, which have all got huge areas of karst. So it's only a local phenomenon in southern Canada because of our climate history over the last couple of million years.
Jeanette, Ben, and Alex ask, can you determine when the next ice age will be?
Yeah, next week. Yeah, that's a good question. If you'd asked me in 1970, I did my graduate work in 1970, and glacial geology was all the rage in Canada then, because you sound like someone who might remember the 70s, and they were cool and wet. And Canada's glaciers began to expand, and I was involved in a project in British Columbia where there was a mine built close to a terminus of a glacier, Barrington Glacier, and they wanted to know whether this thing was going to grow and smother the mine. So we did a whole bunch of field work on the glacier. And the moment I handed in my PhD thesis, the climate started to warm. So there was less interest in climate modeling after that. But at the time, there was a great worry that the next ice age was upon us. And people have been looking at how ice sheets grow. And the old idea used to be they would start in the mountains and then the ice would expand outwards and so on. But that's shown to be wrong. And what you do is literally grow an ice sheet from the base upwards. So you need a succession of wet, cold summers, and all the snow from the previous winter doesn't melt completely. And so you change what we call the albedo, you change the reflectivity of the ground surface, so more solar radiation simply bounces back into space, doesn't warm anything. and you end up with huge snowfields. Labrador, Keewatin, the Northwest Territories, the barren lands, and so on. And these expand and thicken, and they get to thicknesses of several kilometers. So that's called growing an ice sheet from the base up. In the 70s, there was as much concern about global cooling in the 70s as there is today about global warming. Anyway, you asked me about the timing of the next one. It all depends on whether human activity has disturbed the global climate system sufficiently to change things. I'm not sure of that myself, but if you look at the length of previous interglacials, ours is a long one. We're 10,000 years now after the death of the last ice sheet, and normally by now we'd be near the commencement of an ice age. So in a normal world, we'd be getting close, a few hundred years, 2,000 years. A lot of false starts along the way. You know, you can get cool phases, warmer phases, but you know, the question remains about whether anthropogenic warming has changed that. But the basic rhythm, and I didn't mention that in the talk, that's another talk in itself really, but the basic rhythm of ice ages and interglacials is driven by astronomical variables. So it's not driven by anything on the Earth's surface. It's driven by changes in the orbit of the Earth around the sun, and also changes in its tilt axis. These have precise, well-known frequencies. And there was a guy called Milankovitch working in the early 20th century, and he calculated by hand when the Earth was furthest away from the sun. And he said, well, that should be when the Earth is coolest. And he plotted out all these curves, and nobody laughed at him because he'd identified multiple ice ages. And the dominant idea at the time was there only been one. And then in the 60s, people started going out into the ocean basins and drilling sediments, looking at the long cores. And sure enough, yeah, multiple ice ages. I think I mentioned 52. And the timing of them is bang on. It's driven by astronomical cycles. There's a 100,000 year cycle, 40,000 year cycle, 22,000 year cycle, and they combine, and to lower global temperatures. And the effects are most marked at 65 degrees north, because that's where most of the land area is concentrated on the planet. So that's us. That's northern Canada, and that's the home of the biggest ice sheet that develops during an ice age. So we've got nothing to worry about yet, but you never know.
Lynn asked, is this the system being used to map underwater caves that scuba divers explore? The LiDAR.
Not as far as I know, but you could map caves. Yeah, there are handheld units. I'm not aware of anyone that's used one underground, but I would imagine that it's quite easy to do. Even in mining too, design of mines. I can imagine them being used for highly accurate surveying and all this sort of stuff. So yes, but you could check on that. Just put in LiDAR and caving and see what you get.
Jack Campbell asked, how thick was the ice at Owen Sound years ago?
Probably about 1.5 kilometers. That's when it was thickest. And then it would have been like that, maybe possibly from about, well, we know it reached its maximum thickness at about 23,000 years ago. That's because people are finding logs, old tree trunks, other vegetable material that was growing before it was overrun by the ice, and they all come out at about 23,000. And ice got well down into the northern US. And you can calculate ice thickness based on the surface profile of an ice sheet. So if you know where the margin was, you can backtrack up and look at the profile, the slope on the ice sheet. And then the other way to do it is the ice sheet represents a huge weight on the Earth's crust, and the crust is relatively brittle, but it bends by displacing more plastic mantle material away underneath. That's called glacial depression. There's a more complicated term, I won't mention it. That's what happens when students do my glacial course. They get glacially depressed. But then the ice melts and then the crust rebounds, and you can measure like former shoreline orientations because they get warped. So a lake beach, which was originally flat and horizontal, gets warped because the degree of rebound increases north towards where ice was thickest. And it's a relatively straightforward exercise to assess the thickness of ice by the amount of depression and rebound. And again, if you do that, it's about 1.5 kilometers over you guys.
Pamela Kinchin asks, what is it that makes the ice flow? Is it gravity?
Yeah, that's a good question. Think about a bowl of Jello. Take it out of the fridge, turn it upside down, smack it on a table, and the base will start to warm up, and you get water there, and then it will begin to flow outwards because the center of the bowl of Jello is thicker, and the margins are thin, and so it will flow out under gravity and will spread. And that's basically how an ice sheet forms. But we now think that because of these ice streams, it was flowing much quicker, and also the surface profile was much flatter. So if you, I don't want to get too complicated, but we talk about the thermal regime of an ice sheet. And some ice sheets at high latitudes are what we call cold-based. There's no meltwater, it's too cold. So they're frozen to the substrate. So imagine a bowl of Jello that's frozen solid to the tabletop. It's not going to move at all. It'll creep very slowly. Now warm it up and it'll begin to flow. And you warm it up even further and it may even start to stream. And if it did stream, the surface profile would be very, very low indeed. But basically, yeah, ice sheets flow through gravity, but they need lubrication at their base. And I've done a lot of work in the Alps. And you can show that ice velocity increases during the summer whenever we get rain, because the rain will collect on the ice surface and then flow down through it and hit the bed. The bed becomes better lubricated, and you get this short period of greater ice velocity just when it rains.
David Morris asks, what is the typical interval between ice ages?
What's it called, or what is the typical interval? Well, it can be anything up to 10,000 years. Some are shorter. It's all driven again by Milankovitch variables, but the one we're in right now is quite a long one. It should be over. Now, we had this event called the Little Ice Age from about 1300 AD up to about 1900. Things were a lot cooler, and glaciers expanded worldwide, and they reached the largest extent since the last ice age. That's why it's called the Little Ice Age. And there is some debate about whether that might have been a trial run for the next ice age. But it's quite an important event, actually, because it cut off. If you look at the history of exploration in North America, people came over, Vikings, they came over during the preceding warm phase, which is the medieval warm phase. There's much less ice in the North Atlantic, and you could grow things in Greenland. That's why it's called Greenland. They got to East Coast of Newfoundland, Vinland, where vines were growing, and those colonies were extinguished by the beginning of the Little Ice Age, cut off. And that's quite an important event in terms of exploration. Anyway, the point I'm getting to is that when you're looking at modern climate change, it's very difficult to separate. There's a lot of debate about precisely when the effects of us have a bigger impact on global climate compared to natural warming at the end of the last Little Ice Age. So you talk to various people that say, well, it's about 1940. Other people will say, well, it's 1950, 1930. But there is a lot of uncertainty as to when, how to distinguish between warming at the end of the Little Ice Age and what's going on today. So there's still a lot we don't know about climate change, and most of it's driven on the long term by astronomical variables, and then there's also ocean current changes. They're the ones that move. Oceans are the ones that move most of the heat around the planet. We don't have a good idea about how the circulation changes, and it's a big, huge uncertainty in models. So that's the key word, uncertainty.
Pat O'Connor asks, what's the prognosis for the Antarctic ice sheets?
It's probably pretty bad, just because of ice streams. They're pulling so much ice out of the ice sheet, it's not sustainable. As sea level goes up, their flow might increase. They might get better lubricated. And so that will no doubt accelerate. So the future is not bright. It's the same for the Greenland ice sheet too. That's supposed to be melting at unprecedented rates. So it's not a good time to be a glacier right now. But one thing that being a geologist tells you is that things can change pretty quickly. I'm going to say quickly, in thousands of years. So the earlier question about when is the next ice age, that's still looming over us, and in a human time frame it's a long time off. To a geologist it's not. So anything could happen in the next 500,000 years, that could completely change what we're seeing today.
Jan Pugsley asks, what's the difference between dolomite and limestone?
Oh, that's a good one. Okay. Well, dolomite technically is a mineral. And the question ought to be, what's the difference between dolostone and limestone? Limestone is made out of calcium carbonate. It dissolves quite easily. It's relatively soft. Dolostone is limestone that's had dolomite added to it. And you got to remember that all the rocks you see at surface today, the ones you can walk over and see, were once several kilometers underground. And a lot of rock has been eroded off to expose what previously was deeply hidden. And there would have been what we call basinal fluids. That's like groundwater, but with a big difference, like groundwater moving through all the rocks. And once you get a certain depth, they're very, very saline. We call them brines. And dolomite is a very common component of brines, and that would have invaded a lot of pre-existing limestones. And what it does is make a very hard rock. So that's part of the reason why we have the Niagara Escarpment. It's part of the reason why you got that nice topography around Owen Sound, in that the escarpment's not made out of limestone. If it had been, it would have been much more subdued, much more easily eroded, but it's made out of dollar stone. So it's a limestone that was altered at depth by dolomitic rich fluids. So if it wasn't for the mineral dolomite, there wouldn't be a Niagara Escarpment.
Jack Campbell asks, when was the peninsula formed from Point Clark to Michigan?
Well, that's a good question. That's the Door. Is that the Door Peninsula? I can't remember the name now. But the modern Niagara Escarpment is an evolving landform. So it's always on the move. You just can't see it. So its crest is retreating down dip to the west. Every now and then we get a glaciation and the erosion is accelerated, but it's dissolving as I speak. Bits are falling off as I speak. And so it reflects tens of millions, hundreds of millions of years of erosion of softer rocks, shales, and exposure of the harder dollar stones as like ribs. So to say when it formed, it's a tough question actually, because it's still evolving. And if you'd been around 100 million years ago, the escarpment would have been way to the north, because all those rocks are being stripped off, and so the position of the escarpment will migrate through time down dip, down towards Windsor, London, and so on. So if you look at a broad scale view of the geology, we can identify something called the Michigan Basin. And this was a big inland sea at one time, just like a big saucer, several hundred meters deep, several hundred kilometers wide. And the Niagara Escarpment is the edge, almost like the circular edge of a dollar stone unit within the saucer, within the layer rocks within the saucer. And the escarpment is being eroded down dip towards the center of the saucer from all the margins of the Michigan Basin. So to say when it formed is kind of difficult because it's still evolving. I hope that answers the question.
So John reminded us at the start of the evening that you actually had spoken at the Field Naturalist about 10 years ago. You were in Owen Sound in the library.
Oh yeah, that's right. I'd forgotten about that. Yeah, you're right. I forgot what I was talking.
Point out the venue that we hosted you in back then, unlike the venue today, the venue in the library was not licensed for the alcoholic beverages, like today it is. Like,
well, I'll drink to that.
So Bella Waterton is curious whether there have been some interesting Min-X implications or deposits discovered due to the updated flow mapping.
Oh, that's a toughie. The industry is grappling with this issue right now. You know, all exploration work is model driven, and I have a colleague that says all models are useless because it's mostly a matter of luck. And so you have deposits that have been found supposedly by the application of this model or that model, you know, to make it look more intelligent than it actually was. And the industry is grappling with this new ice stream model of ice sheets. It's a tough one because the indicator minerals are transported very much further. You get a different shape. We call them dispersal fans. I'm not sure if I mentioned that in the talk. Dispersal fans. It's the actual shape. If you imagine if you're up in a satellite looking down the Earth's surface, the shape that the dispersed minerals have when they've been eroded away by ice and transported. And if you're underneath an ice stream, the dispersal fans long and narrow. If you're under ice that was flowing much more slowly and spreading more slowly, they tend to be much more broad. So it does mean that you can miss dispersal fans quite easily, because they do tend to be narrow as a few tens of kilometers, even if that. But that's quite a difficult question, and there's a lot of research going on right now in universities and industry to try and come up with a working model. But in the past, there's been lots of mines found as a result of what we call drift exploration. Drift is a bit of a funny term. It's an actual 19th century term that was used for all glacial sediments when people didn't realize that they'd been deposited by ice sheets. They thought they'd been left by floods. Drift. And it's still used. We talk about drift exploration, but there's lots of examples of good mines that have been found, and diamond mines too. There's, I think, 3 or 4 in Canada, and by and large they've been found by traditional exploration using drift models. So there's a PhD thesis waiting to be done if you want to do it.
So Jim Coles says, I live on a farm within the Erin Amabel drumlin field. How are drumlins formed within the ice flow?
That's a good question. They're probably the result of erosion. So most drumlin fields tend to be in valleys, depressions where sediment was deposited, probably by rivers, probably by large lakes dammed up as the ice came in, and then the ice erodes it. And forget what an individual drumlin looks like. You've got to think about the surface as a whole, and it's something we call texture. So that surface is a low slip surface. It allows something else to slide over the top. And so a drumlin field allows ice to move much more easily over that surface than if it was a flat surface. So it's the ice trying to engineer its bed by lowering basal drag, lowering friction at the base, and a streamlined drumlin, and the drumlin field as a whole is a low slip surface. That's what we'd say. If you had somebody else answering your questions, they might say, well, they're depositional, they're built up in place. I don't think that. If you look at the geology of them, there's usually much older sediments inside them, in their cores, and you can see that they've been truncated by the modern surface, the land surface. And there's an enormous literature on drumlins. It goes back to about 1830, actually. It's been a fascination with these things. Enormous literature. And I know perhaps most of it, and I'd have to say that most of it is in favor of an erosional origin. But that, again, it depends on who you talk to. There's other groups out there that say they're depositional.
David Morris asks, how much longer will Ontario continue to rebound from the weight of the ice from the last ice age?
That's a good question. If you're in the southern part of the province, it's already over. As you go up near Owen Sound and places north, it's, what is it? A few tens of centimeters every century, top end of Parry Sound, and then you get up into Hudson Bay and it's coming up pretty fast. And that's simply because, as I touched on earlier, there was thicker ice to the north. So in places, like Toronto, where ice wasn't very thick, then rebounds over quite quickly. Owen Sound, where it's a little bit thicker, rebound's still going on, although it's almost over. The top end of Parry Sound is coming up. So the whole of the Lake Huron, whole of Georgian Bay is the bedrock is slowly being tilted down towards the southwest. And then if you go further north, that process is quite active, particularly around the shoreline of Hudson Bay. If you go up to Polar Bear Provincial Park, anybody been up there? That's where Ontario is gaining in size every year because the coastline's being uplifted, and there's all these beaches now above sea level, and it's all because of post-glacial rebound. So the answer to that question depends on where you are in relationship to the center of the ice sheet. If you're in an area which was close to the center where the ice flow was greatest, the rebound's still going on. If you're in an area like Toronto where you were fairly close to the margin, it's done and dusted. And that has implications too, because sea level's on the rise. So a lot of Canada's southern coastline, British Columbia, Nova Scotia, Newfoundland, there's no more rebound. It's finished, but there's sea level rise. So we have what we call a transgressive shoreline, where the shoreline wants to move inland, there's erosion. And that's completely different to the situation, say, at Polar Bear Provincial Park, where there's a regressive shoreline, where the shoreline is actually moving offshore as the land comes up. So that question has some practical implications in terms of protecting towns, cities from sea level rise.
So Jan Pugsley asks, she says there's a dune system on the Bruce Peninsula and further south. It's in the news today in these days is Sauble Beach. Why sand?
Yeah, they're interesting. I do have some, I don't know if you've ever seen a book that I put together. I edited it a couple of years ago on Georgian Bay. It's for the Georgian Bay Georgian Bay Land Trust. It's published by Fitzhenry and Whiteside, but there's some nice images of the sand dunes and strong wind, probably there were large lakes in that area. So where there is now Lake Huron, there was a big lake called Glacial Lake Algonquin with a surface tens of meters above the modern lake, and that drained, and huge areas of sand were exposed. The wind got hold of it and made that pretty impressive sand dune field. And it's still today, you got a lot of very easily eroded sand sediments up there, and they move around in the wind. So that's part of the glacial story as well in many ways. I got a question for you guys. Why has glass been made in Owen Sound? Why is that? I've always wondered why. What's that sand factory? The glass factory.
The government. Can you hear me?
Yeah.
The government in the 60s gave money for factories to come in because it was a depressed area.
Oh, I see.
And so it's Pittsburgh Glass and
Yep.
the brake shoe people. What's that? Monroe.
Yep.
And there was other ones as well, but that's, well, yeah, RCA got a new building, but they had been here. That's what brought me to Owen Sound.
Oh, is that right? Oh, that's interesting. So all the silica and the quartzite was brought in by Great Lake steamers, I guess, right?
Yeah, I would guess, yeah.
Yeah, that's interesting. I've always wondered. Yeah. Right. Thank you.
All right, so I think just this is the most questions Q&A we've ever had for a speaker, so this is fantastic. Just
Sure.
2 more questions from us, and then if you have more questions to ask us,
Yep.
we can do. There's a hot hack. I'm not sure what their name is. Is there a new book in the works to follow local stereo?
Yeah, there is. Yeah, I'm just finishing it now. Actually, it's going to be published by University of Toronto Press in the fall next year, and it's a book about a famous Canadian geologist called Jock Tusa Wilson. And my question for you is, who was Jock Tusa Wilson, and what was his big discovery? You have 15 seconds left.
Can I phone a friend?
Hang on. We might actually have Nora.
You can consult amongst yourselves.
Nora, if you know, you can unmute yourself.
Jock Tusa Wilson.
Well,
He was once.
Tusa Wilson was at Arundel College when I was there. He was the principal of the college, and he's famous for continental drift.
That's right, exactly. Yeah, and very few people have heard of him nowadays. So I was, every summer, I take members of the public on a rock walk on an island in Georgian Bay, and we choose a different island every summer. We have a lot of fun. It's like D-Day. A whole load of boats show up and we invade the island and we look at the rocks. And I gave a talk out there one year, and you can't help but mention the name of Tusa Wilson if you're talking about geology, because the geology of Georgian Bay only makes sense if you know something about supercontinents and where Ontario was, hundreds of millions of years ago. Anyway, I had finished my spiel, and somebody came up to me and touched me on the elbow. These were pre-COVID days, obviously. And they said, "Oh, his daughter's standing over there." And I was flabbergasted. And she's well in her 80s now, Susan. And you might remember her, actually. She would have been at Arundel with her father. And so I ended up having a long conversation with her. And she told me that she didn't really know what her father was doing when he was making his big discoveries. And I only learned later when he died. And that he'd written an autobiography, and she tried to have it published. And I said I'd take a look at it and see what needs doing to it. But it's very thin, and he was a very modest person, despite his prominence. And he glosses over what his contributions. There's a lot of stuff on his wartime exploits. He was in the Canadian Army as an engineer during the war, served in Europe. But when it comes down to his major discoveries, there's like 4 pages, and I actually don't think he wrote it. I think it was his wife that put it together after his death. So she was frustrated that his story wasn't out there. And I thought, well, yes, that would make an interesting book, actually. And it's been fascinating. I've been working with her. We're in touch almost every day. She's just going to send me a whole bunch of letters that she's just come across. There's a wealth of material, and it's been one of the most interesting projects I've been involved with. So it's to make people aware that we in our midst we had a fantastic world-class scientist, and it's interesting. It's a fascinating story. His parents were equally as fascinating as he was. His father basically developed civil aviation in Canada after the First World War, and pioneered the use of air photos like LiDAR for mapping Canada. And it was used in mining mapping up in the north. And then there was a big debate. You mentioned the word continental drift, and there was a big debate raging in geology between two competing tribes, the permanentists and the mobilists. And the permanentists believe, they're mostly American, they believe that the continents were fixed. They could grow in situ, but basically they found where they were formed, and that the oceans had land bridges running across them that enabled animals and plants to migrate between continents, and the land bridges would collapse. And then there were the mobilists, mostly this German Wegener. And he argued that for continental drift, and he was basically shot down, all sorts of interesting reasons, mostly because he was German, and he published his theory just at the end of the First World War. And anyway, it's not until the late 60s that he was vindicated, largely because the US Navy, the Royal Navy, mapped the ocean floors. It was a Cold War, and they were looking for Russian submarines, and so they had to know the topography of the ocean floors much better. And we basically discovered how the planet works because of that. So it's a fascinating story. But my problem is it's addictive, and I have to draw the line somewhere and say that's it. I'm not writing anymore. So. I got an email from U of T Press saying they want everything by the end of January, and it's going to be out in the fall. So, but I'd be interested. Did you actually know Tusa Erindale?
I wouldn't say I knew him, but I certainly I studied under Roger Byrne. I don't know whether he went to California, I think, but I've been to his house. His house was on the campus, and I think we had maybe one party or two.
Yeah, I mean, if you've got any interest in anecdotes,
no. I wish I did.
There's about a dozen people that have approached me and told me their story about how their careers were changed by basically 5 minutes with this guy or just listening to a talk, and it's fascinating. But his name's been lost, and so this is an attempt to put him back where he was. At one time, I'd say Canada's most famous scientist.
I would agree with you there. Yeah.
He went to the Ontario Science Centre. Was it 74. He was there for 11 years, and he was. I don't think he was the founding director. I think he was actually the second director. But he had that big exhibit on China. He was fascinated by China. He wanted to know why they hadn't had an industrial revolution, and why they had no imperial ambitions. Although that's changed. So he spent a lot of time there. He wrote a couple of books. Got to places where other Westerners never could get to. So he's a fascinating guy, and then his wartime record is equally as interesting.
So one last question from us, from John Dixon. I learned one of your books about the fault down the middle of Lake Superior. Are both sides of the fault line changing elevation relative to each other as the plate below moves 4 centimeters to the west each year? I understood that the fault is opening up a little, and I'm curious about what that looks like, 5 or 10 feet width, or less or more.
Yeah, that's a good question, because we have these very old structures. You got to remember that the geology of Ontario has been put together over 3 billion years, and so we've got these old faults, and they never really heal. And some of them were like the San Andreas fault when they were forming. They were at the margins of blocks moving past each other. And so the story is that, the North American plate is moving 4 centimeters westward. It's about the thickness of a piece of paper every day. And so these faults get reactivated. And if you plot earthquake epicenters in Ontario, and there's a lot, you'd be surprised. They all seem to fall along these old buried faults. And that's the key issue, that a lot of them are under glacial sediments. They're under limestones. So the Niagara Escarpment, you know, if you were to drill down, you'd hit the shield about 300 meters down. And so there's some areas in Ontario around Oakville, right at the western end of Lake Ontario, which are fairly active actually. Oshawa, and people have mapped these earthquake epicenters and found that they do coincide with these very old, deeply buried structures. And that's, interestingly enough, where LiDARs come in, because it does look, you know, you say, well, why do we have Great Lakes? Why do we have rivers? And if you look at where they are, they don't occur where they are by chance. And very often they follow weaknesses in the crust, because it was more easily eroded. So the fact that we have faults along the axis of the Great Lakes is not really novel. It's simply that the Great Lakes could be hollowed out by glaciers much more easily because of these faults. And we have some LiDAR data. I think I showed them in the talk towards the end from Kingston, at the eastern end of Lake Ontario, and you can see in much more detail and more frequent faults than we've been able to map previously. So LiDAR, you know, probably in the next 10 years, 20 years is really going to revolutionize understanding of earthquakes and faults in Ontario. But again, it's all dependent on availability. It's a very patchy availability of data. But it's fascinating actually, because you can, with LiDAR, you can strip off, you get the data is so great, you get what's called a point cloud, and you have to classify the data within the cloud to get layers and so on, and you can remove layers, and so you can remove vegetation, you can remove urban areas. So I have the power now to remove the whole of Owen Sound if I want. And I'm joking for Owen Sound, but we've done this for Toronto. You can get rid of all the urban infrastructure, and you can look at the landscape underneath, and you can still recognize original glacial landforms. But it's unfortunate that the data is only sporadically available in Canada, and then you need a lot of computer processing. You need a lot of storage space too. The amount of data is just huge before you can come up with these beautiful images. But like everything else, it's I think people are now appreciating the value of LiDAR for surveying, agriculture, construction. And it's now very rapidly becoming an everyday tool that you need. So I think Canada ought to have a plan where we fly the whole place with LiDAR. I think it should be a national plan. But anyway, that's in the future.
Okay, well, I think that has pretty much exhausted our questions for now. So I think we should have you back maybe in the fall and do another talk for us. Everything is quite fascinating.
Yeah, hopefully live. Yeah, let's do that.
Yeah, live would be wonderful.
It would, wouldn't it?
Good. Yes, it would. Okay, well, in the news, as we know, everybody looks like they're starting to think about inoculations. I just want to warn you, you have to get 2, and I'll be one of the first ones to get them because of my work.
Right.
And it's not so nice, but we're looking forward to it. And hopefully we can see each other a lot more in the next little bit. So yeah, I think on that note,
I really appreciate the invite, and I've enjoyed the talk and the questions have been really good. And I'd love to come up and give another talk whenever we from under this contagion. So in the meantime, in the absence of a vaccine, I stick to wine.
I think that's a really good idea. Anyways, I must say good night, and I hope everyone has as much of a good Christmas as you can. Get your
Thank
baking
you.
done and your presents wrapped, and hug who you can.
Yes,
Good
all
night,
right.
everyone.
Stay safe, everybody.
See ya.
Good night.
Good night.